and mechanism dynamics. Behavioral modeling extension deals with the function aspect of the design. You have fit, form, and function for every design. And function is something that's often ignored and obviously realized at the very end. So how do we go about optimizing our design for it to function correctly? So to explain you these details, I have a few examples from, like say, an airplane wing to a hand pump to where I use Excel to drive my model using equations in Excel or MathCAD to other types of analysis like say user defined and stuff like that, right? So I have a variety of examples to kind of cater to different types of industries. In this particular example, I'm just going to try and give you a basic overview as to what you can do with behavioral modeling. So what I have here is a little bicycle, and you notice that I'm using blocks for arms and body to kind of like have them for loads on the handle and on the seat. Now, my aim here is to make sure the center of gravity of this system kind of lies exactly between the two axes, between these two locations. So what I'm going to do is I'm going to try and create a plane and kind of like move it exactly between the two locations. So I'm going to use an equation, say d0 by 2, so that d0 is the distance between those two axes. I'm placing it right smack in the middle of it. All right, so next thing I'm going to try and do is find out where the center of gravity of this system lies. So I run a mass property analysis, and I go save it as a feature. You could see right here, that's where the current center of gravity of this entire system lies. So I want to create a point over there, and I want to call this feature COG. Okay. Now I'm going to try and measure this distance between where the current C of G is and where I want it to be. Now that distance is 3.02. And now what I can do is I can save this as a feature. I'm going to call it distance. I do this so that I don't have to keep editing the feature to look at the value. I can also go to tree columns and add this parameter so that it always displays the value for me. Now my aim here is to minimize that value to 0. So in order for me to minimize that value to 0, I have to change a few dimensions in the model to make sure that the system's CG moves. So let's say we run something called a sensitivity analysis. In a sensitivity analysis, I can go ahead and pick a certain dimension. Let's say I pick the angle dimension and I want to vary it from say 70 to say 80, and I want to plot how this distance between those two locations change. So you can see, as in a graphical way, it's going to pop up. You can see as I change the value of that dimension, how the distance changes between those two point and the plane. All right, so I can go ahead and try different dimensional values. So I can pick that. Say I want to go from 24 to 29, and I want to now plot how this distance changes. So if this graph ends up being a straight line, that means if you change the dimension, your parameter is not getting affected. In that case, you might not use that particular dimension to optimize this model. All right. So what the sensitivity study gives me is it gives me the range for the dimension, and if I should pick this particular dimension as a design variable. So what I can do right here is I can say I can optimize it, or I can run a feasibility analysis to kind of find out where my solution lies. So I'm going to go ahead and say I want to add a constraint, design constraint. I'm going to say my design constraint is that distance is supposed to be 0. Okay, that's my design constraint. The dimensions or the variables that I want to change is that dimension. I want to change it from say 26 to 30. I want to change this angle dimension to go from 75 to 85. And I want to pick another dimension here and change that from say 16.5 to 20. So I'm varying these dimensions, making sure that the distance between the point and the plane is minimized to 0. So when I run this particular feasibility / optimization analysis, it's going to come back and tell me for what values of these dimensions you get this center of gravity point moved to exactly in the center of the two axes. You can see that I got different values for my angle, that distance over there and here, and you see my distance value went to 0.00004. Now when I close it, I can confirm to keep it. So now you have your center of gravity lying exactly in the center between the two axes. So this is like just giving you an overall gist as to how behavioral modeling works, right? Now, yes, the cycle is structurally stable, but is it supposed to function the way it's supposed to is more or less determined by behavioral modeling. You can also run a lot of what-if analysis. So when you have a new design, you want to try out different variations of your design and see how different factors get affected. You can run a lot of what-if scenarios too over here. Now, I have another example right here talking about user-defined analysis. So let's say we design this little pipe, right? So, or you can call it like a, valve, whatever, like, something that you're going to use with respect to, say, engines, you can use with respect to pressure vessels, so on and so forth. Now, let's say my aim here is, yes, this design is good, it's manufacturable, it fits well in my assembly, but is it going to function properly? For example, because this is, you can see it's a surface model, I'm more curious if the change in the cross-sectional area of this pipe is uniform, or is it, how do I put it, is it like changing or not uniform, to put it like that, okay? So here I'm also going to talk to you guys about the importance of creating field points. So you have a field point right here. Field point is generally used in analysis. I'm going to go ahead and position this field point on this particular curve. Right, so what I have right now is a little field point right there. Now I'm going to go ahead and create a plane passing through the field point and normal to that curve. So there you go. Right, it's passing through the field point, normal to the curve. Alright, so let me go ahead and hide these other stuff. I'm going to create a sketch on this plane. So let me use the field point as a reference, and I'm just going to stick in a circle. Alright, so here's my circle. I'm going to select that circle and create a surface by using the fill feature. Now you can select both the quills and say, merge or trim. So there you go. So you trimmed it. Now let's go measure the area of that patch. So there's your area. And let's go ahead and save it as a feature called area 1. So what I want to do is, as I travel along this pipeline or this duct, say air duct or whatever, I want to see how my cross-sectional area changes. So what I'm going to do is I'm going to select all the features that I've created and put them in a group, and I want a column. Let's go rename it to say air duct. Okay. And what I can run right now is a user-defined analysis. So I can pick my air duct group and say compute. What this is going to give me is the minimum value of the cross-sectional area. All right, the maximum value of it. You also get to see a graph as to how this area is varying. Do you have any sharp corners in this graph, right? So just so that you determine how the flow is going to be. Okay. What you can also do with this graph is that you can also look at, instead of looking at the entire curve, you can look at a select point and get the value. So it says I go ahead, select location, and say at that location, the cross-sectional value is 67.79. I can go ahead and pick another location and say at that location it's 169. So you can select a point and get the value for area, or you can go with the entire field and get a graph with it, trying to show you as to how the area changes. So if you see that in this particular graph, how the area gets flipped down the other side, and you can see how it's changing. If that graph is not smooth, or if this curve settings are not smooth, you can see right here, you can go scale them, right, and do some other things with it. See that? You can scale, and you can see if the graph is smooth or not. So this kind of gives you, basically, see that? In compute, this kind of gives you how your cross-sectional area is changing along the length of that particular pipe. Okay. Now this could be very important input into, say, some flow calculations. Alright, so that was kind of like another different example. So I wanted to show you, started off with the process, went with like a user-defined analysis and how you can use field points to do that. Okay. Next I'm going to get into, say, a wing, a lift force optimization for an airplane wing. Right? I work a lot with RC planes, so this is something that I use too. So here I have a little part. So let me just get this out. So let me suppress those. So here's my little wing part. Right? So obviously the plane's kind of flying in that direction. So when you look at it in the direction of the flight, you can see how your cross-sectional area, which is projected onto this particular plane, looks like. Okay, so that's my wing. First and foremost, what I'm going to do is I'm going to go ahead and measure the area. So I'm going to go pick from the list, pick the entire wing part. So it's the entire cross-sectional area. And then I can say, okay, I want the area projected onto this plane. So you can see the projected area is much smaller. So if I look at this wing normal to that plane, that's the area that it's going to interact with the wing. So here I'm going to go ahead and see, I have my projected area. I'm going to save this as, say, area 1. I'm just going to save this feature. And I can always find out the value by going through feature parameters right here. And so that's my value. Next thing I'm going to do is I'm going to run like a analysis feature right here. I can say this is lift force calc. Okay. I'm going to say I'm going to use Excel to find this calculation. I go next. And here I'm going to load my Excel file. Just give it a second. And right here I have two buttons. I can create new or I can use an existing file. So I'm going to load it. So here's my wing calculation Excel file. All right, so you see that I'm using the angle of attack, I'm using the projected area, air density, air velocity, wing speed, and lift coefficient to calculate the lift force. Okay. So what I'm going to do is I'm going to try and push certain dimensions and parameters to Excel, and I'm going to read certain values from Excel back into Creo. So I'm going to say add a dimension. I'm going to pick on this and say, okay, I'm going to pick that dimension. 10, you can see that's the angle, and I'm going to push that to the angle of attack value. You can see, so this dimension D17, value is 10, is going to cell E16. Now I also want to push a parameter which is projected area, which we calculated from area 1, you can see right there, projected area, and push it to this cell which is projected area. Right, so you're pushing a dimension and a parameter, and what I want as an output from Excel is the lift force. And I can say compute. So there is the value of that lift force. Now I say close. I'm going to name this as lift and say done. If I want to know what is the value of the lift force at all times, I can go feature parameters and type in lift. So there you go. Now, how do I go about maximizing this lift force? So I have to change the angle of attack of this particular plane, wing, to say which particular angle gives me the maximum lift force. So for that, I'm going to run a sensitivity analysis to say the dimension that I'm going to try and vary is this value, 10. I want to go from 0 degrees to 20 degrees. And the parameter that I want to plot is the lift force from the lift force calculation analysis. And say compute. So what it's giving me now is it's telling me as I change the angle of attack on that wing, how the lift force changes. So you can see somewhere around 15 to 16, I get some max value right there. You can see it's 77 point something, right, at a certain value. So I say, okay, that's the value. So let me go ahead and optimize my part. Okay. So how do I go about optimizing the part? So I go parameter that I want to constrain is the lift force should be greater than or equal to 7,500. Okay, I want at least so much of lift force. That's my constraint. Dimension that I'm going to change is that I'm going to change it from say 15.4 to say 16. Okay, so you can see when you change the angle of attack, the projected area obviously changes, which can affect the lift force. So I'm going to go ahead and say compute. So notice that because of my sensitivity study, I could have a smaller range for my design variable instead of having a larger range and waiting forever. So I go compute this. So it's going to run the calculation and say, okay, 77.24. 7724.15 is the lift force that it could optimize to. Now again, when you optimize it, you can see that you have a certain convergence percentage, maximum iterations, and what method you want to follow, like you want to follow the GDP or not. Okay, so you have different values or preferences that you can set. So now when I say close, I can say confirm to keep it, and there's my maximum lift force. There's my maximum projected area, and that's the angle of attack that I need to have to get max lift. All right. So those were some 3 examples that spoke about behavioral modeling, and now I'm also going to use another example to optimize volume, right? Let's do some volume calculations. So I'm going to go ahead and open an example for volume and kind of go with that. Okay. So let's say fuel tank. So here in my fuel tank, I want you to see that I've created a plane right there at the very top. Let's say I'm going to call it the fluid level. Okay. Now I have created a measure which is volume of solid. So if I do an edit definition, it basically says measure the volume of solid below this particular plane. Okay. One-sided volume. Now similarly, I've shelled the model and I'm measuring the volume of the same part below that plane after shelling. Now, if I run an analysis, which is basically a relation where I say, okay, volume of the solid minus volume of the shell should give me the volume of empty space in that particular tank. I'm dividing it by 100,000 to kind of give me the volume in terms of liters. All right. So let's say, what is the volume? So I go 3 columns and say, okay, display the volume. So you see it says 0.33 liters. So let's say, what do I need to do to increase the volume to 0.35 liters? Okay, so I'm going to run a little sensitivity study. Say the dimension that I want to vary is that. So I'm going to vary it from say 58 to 62, and the parameter that I'm interested in is volume of fluid, and compute. So it's going to tell me, all right, so what should be the design variable value to move this or increase this volume from 0.33 to 0.35. Now you might also have a bunch of constraints where say, okay, you cannot increase or decrease the thickness of this tank, right? Those could be certain constraints, okay? So you can see 0.35 value is attained somewhere close to 61, okay? So that kind of gives me a 0 or lets me zero in on certain values for my answer. So now let's go back and say we're going to optimize this part. Say my idea is to maximize the volume of fluid. That's my goal, maximize the volume of fluid. Now I can also say the volume of fluid needs to be equal to 0.35. That's what I want. Okay. Now I want to add a dimension and say I want to vary it between 60 and 61. Oops. 61. I can do a smaller range because I know where the answer is from my sensitivity study. And I can go ahead and say compute. So what it's going to do is it's going to try and optimize to maximize the volume of the fluid. And we have a constraint saying that the volume of the fluid is supposed to be 0.35. So here is your optimization convergence. You can see that it's a straight line. Okay. So I can say go ahead and close that. You can see at 60.95, this value is 0.350031. Close and confirm. So now, let's say I want to know where the halfway mark is, or I want to know where is 0.175 mark, right? I want to know when the tank is half full or half empty. So we can go ahead and say, I'm going to run a sensitivity analysis to where I'm going to move this measuring plane from say 30 to say 50, and I want to compute the volume of fluid. So what I'm doing now is I'm just moving the plane or the marker down. So now I know 0.75 is somewhere around here. Okay, and that value is between say 34 and 35. So we can go say maybe hit 34 to 36. So we can go optimize. Say I want the value of this volume to be 1.75, and I want to vary that tank dimension from say 34 to 36 and compute. So you can check here at 34.34, you see how only the plane moved down. The value of this particular marker is exactly a halfway point, right? So these are some of the calculations that you could do using behavioral modeling to kind of run design studies on your model. What I'm going to try and show you next is a combination of motion analysis along with some behavioral modeling. Okay, so let's say we get our hand pump right here. Okay, so I want to go to applications mechanism. You can see that I have a simple little position analysis which kind of does that, right? So I want to know in one stroke how much of water or whatever is being pumped, right? And I want to see how I can change certain dimensions to optimize this D. So first and foremost, what I'm going to try and do is I'm going to try and find out what is the distance between the end of this pipe right here and the piston, which is kind of like stuck in the water or whatever. So I go distance from there to there. Okay, and I want to know the distance in the y direction. You can see x, y, z tells you in the delta y what is the distance. Okay, you can see all the parameters that it's going to create, and I can go ahead and save this feature as distance. Right. So next, as I move this pump up and down, so you can see if I go drag this pump up and down, you see how there is interference right there. So I want to make sure that there is some kind of a clearance between those two parts. So what you can do is you can measure the clearance between parts. So I'm going to say clearance between that part and that part. I want to save this. You see it creates a clearance parameter. So you can go to 3 columns and say feature parameters. You can show clearance as well as the y distance. I kind of forgot to make a note of that. It says distance y. So I can also go ahead 3 columns and show the distance y in there. All right. So now I want to go ahead and run it through the range of motion and kind of find out how this value for distance between those two change per stroke as this piston moves up and down, and I also want to see how the clearance changes between those two components. So I'm going to run an analysis. I'm going to call it, say, range of motion, okay, and say this is a motion analysis. Next, you see I want to plot the distance and the clearance, okay, and say run it. So you can see how the clearance changes through the range. So notice it's not below 0, so there is no interference. And you can also see the maximum distance y and the minimum distance y between those two surfaces. So if I can do my volume calculation, because this could be like the height of the cylinder, which would be the difference between these two distances, I can calculate the amount of volume of water being pumped out. All right, so I'm going to say close and say I care about the minimum distance y, the maximum distance y, and I also care about the minimum clearance between the parts, and say done. Okay. Now let's do another analysis where, say, this is going to be a volume calculation. So I'm going to go volume calc, say it's a relation, say volume equal to, all right, so you can say max distance y colon feature ID range of motion minus minimum distance y colon feature ID range of motion times pi. And say done. So we can also go ahead and get another parameter called volume. You can see what that value is. So what I did is, when I ran this range of motion analysis, I kind of calculated this distance d from minimum to the maximum. So now I got the height of the cylinder. Now I can just subtract this distance to kind of get the overall volume. So it gives me a volume of 27.88, right? So now my aim here is to maximize that value, okay? So how do I maximize that value? I can run a sensitivity analysis. So I can say, okay, let me go ahead and increase the length of that link. So let's say I'm going to change that link from 8 to 10, and I want to plot how the volume changes in 5 steps. So it's going to run through the entire motion, right, for different values, and you can see as that link length value changes from 8 to 10, you see how the volume of water pumped increases. So I can definitely use that value in my analysis, right? So now similarly, I can also go ahead and run some more sensitivity studies in terms of the distance between that hole and that hole, right? And we can plot how the values change. So let's go ahead and run a little feasibility study. So a feasibility analysis, okay? Or we can also run, say, optimization, where you can say I want to maximize. See, the difference between optimization and feasibility is that feasibility does not have a goal. optimization has a goal, right? So here I want to say maximize the volume, okay? Now the parameter that I want to add as a constraint is that I want the clearance to be greater than or equal to 0.25, right? Clearance is the distance between those two. I want that clearance to be greater than or at least equal to 0.25. Okay, that's all I care about. Now my design variables are, say, that particular dimension right there, and say you change from 6 to 10. I can also add the overall length of this link and vary it from, say, 18 to 22. I like that. You can also go ahead and pick this particular hole. So move that hole so that the pin or the link gets connected at different locations, and move that between, say, 5 and 10. Okay. So I have these three design variables, and I can go ahead and compute. So what it's going to tell me is it's going to optimize to maximize the volume of water being pumped. It's going to make sure that the clearance is at least 1/4 inch. It's going to change these dimensional values to make sure in one stroke I get max amount of water pumped. So this is optimizing your design to improve the design in terms of functionality of it, right? So here's again an example for the function aspect of the design. I might actually get away without changing the overall length of the link, but the reason I'm changing the overall length of the link is because the hole's position is relative to the overall length. So here it's still optimizing the part. You can see it was doing about 27.88. Right now we are hitting close to 40 in the same one stroke that you were doing. So while we wait on it, you guys can kind of like, you know, go through this overall process in your head. Like, say we measured the distance so that we can do a volume calculation. Can be also calculated the clearance, so we can keep a minimum clearance between those parts to avoid interference. We had a range of motion analysis, which was, say, this would be one stroke, right? And then we just did a relation to calculate the volume. So I think that it's pretty much hitting like a straight line. It's plateauing down, so it's going to run a couple more iterations to make sure that it cannot further improve the design. So as you see that the values kind of are very close to each other, it's going to say, okay, the solution converged, and this is the correct answer for it. Okay. So let's give it a couple more seconds. All right, so you see that it says part was successfully optimized at the bottom of my screen. You see that it kind of stopped, right, because it cannot further improve the value. And you can see that if I say close and say confirm, it's going to keep the values. You can check the length values changed. You can see that particular part. So if I go ahead do an edit on it, you see right now that's at 10. Okay. You can also look at the handle assembly. You can look at that, and you see that value is at 9.39. Earlier it was 7, right? You can also see the overall length of this linkage changed. It used to be 20, it's 8.11, right? So that's another example to show you how we can optimize certain things in terms of design. Again, we're not talking structural optimization in terms of FEA. This is design optimization. All right, so that's what I had for behavioral modeling. I also have a couple of other examples. For example, like, for mechanism dynamics, you see that I have like a little backhoe right here. Again, this is not a design, this is all connected through connections. You can see there's a slider connection here, there's a pin connection here. So a bunch of connections right here. And when you get into mechanism, you can also add things like, say, motors on these connections. You can see right here, there are some motors. You can also add forces. So you can see, add a force on that, which could kind of like say that would be the weight of the mud that that this backhoe is going to go pick. You can have some initial conditions, say like, this would be the start position where I take a snapshot of this particular assembly. And you can also run analysis where you can pick, say I'm running a dynamic analysis. I have certain motors which run from start to the end. I have a bucket load right here. You see that it's varying from that to that. You also have gravity. You can enable friction. You're right here is your bucket load. And you can go ahead and run it. So you can see that only acts from 11.4 seconds to say 17 seconds because that's when it's actually going through that motion. So before that, it's not actually going through that motion. Okay, so you can see how you can do that. What you get out of it is also like graphs. You can go ahead and say, hey, you know what, I want to know the connection reaction over there in terms of radial force, and I can measure that. So you can see how the radial force changes. So you can run a ton of measures. One of my other favorite part of this mechanism dynamics is the force balance analysis. So let's say, for example, we have a situation where we have something like this. Okay, so you can see that this particular part can move up and down, and when this part moves down, this is supposed to push the ball in, which is supposed to push the screw out. Okay, so I'm getting into mechanism. You see, as you go in mechanism, you can create springs. So you can see right here, I've created a spring between those two parts. See that, the ball and that. I can tell it that it's a torsional spring or an extensional spring. I can give the stiffness value. I can give the unstretched value of the spring. So you can see the current value is 1.116, and the unstretched value is 152. So you can see there's a little bit of tension in the spring. You can also create cam connections between that ball and this little surface so that it can slide. And you also notice that we can go ahead and add forces. Like say I'm putting a load, right, on that point right there so it can push down. So for dynamic analysis kind of tells you the connection reactions and all those kind of good stuff. What a force balance analysis kind of tells you is like, when I push this thing down, that ball's going to push the spring in. Now, what force balance analysis tells me that how much force should be applied from here inwards so that that ball stays in place. Okay, so it's an opposite of static analysis. So you can see when you run like a force balance analysis, you can create a load cell. So I can say load cell at that particular point right there, and you can say, okay, what is the X vector, what is the Y vector, and what is the Z vector. Okay, so you can have load cells. You can see that I have one more right there just to show you. I'm going to go ahead and hide that part to see to show you as to what is this load cell measuring. So you can see the load cell is actually measuring the force exerted inwards by the part that was moving down. Okay, that's what a load cell is going to measure. So when I run this analysis, it's actually telling me that the reaction force is 121. So that's the force I have to apply in the opposite direction to stop this thing from moving down, right? That's an opposite of a static analysis, right? So it basically tells you what should be the load applied to hold the system in place, you know, in terms of, you know, when gravity or certain other forces are acting. Okay, that's a force balance analysis. You just end up creating a load cell to kind of find out what should be the load that you have to apply in the opposite direction to stop this particular part from moving down, right? We have plenty more examples, but we are hitting close to an hour. So I'm going to stop right here. If there is more interest in these kind of analysis types, just let us know through the poll or contact Jason for that, and we'll do a more detailed only based on mechanism dynamics at a future date. So thank you. And Jason, you need to unmute yourself to speak, buddy.
Thank you, Sukumar. Let me take back control here. Thank you, everybody, for attending the webcast today. We'll send out links to the webcast afterwards, so you can come back and watch it again afterwards. All webcasts are always viewable on our website. If you go to the webcast and view Archive webcast, as well as our YouTube page at www.youtube.com/customer-driven-tech. For those of you on this, if you don't know already, there is a 50% off simulation software, TLO, going on currently through the end of next month. If you have any questions, please contact your local sales representative or myself, and I can put you in touch with them. As far as training goes, we do have training classes regarding what we've covered today in our Kansas City location in August for behavior modeling, mechanism design, or mechanism design simulation. Please reach out to me. We can also add in some of our other training centers if need be. And if you have any questions, like I mentioned, about training, or you don't know who your local rep is, please reach out to me and I'll put you in touch with them. And you can also reach out to Sukumar if you have any questions. Thanks for your time.